If you picture electricity moving through a wire, you probably imagine a perfect, uniform stream of charges flowing steadily from point A to point B. This total volume of flow is what we call macroscopic current. In standard equations, it's represented by the simple scalar variable, capital I. However, this macroscopic scalar fails to account for scenarios where charges distribute unevenly across a wire's internal geometry. Take a look at this cross-section. Here, the charges are packed tightly and moving rapidly at the central core. As we move out toward the edges, the flow thins out and slows down drastically. The macroscopic value, I, is completely blind to this internal variation. It only measures the final output coming out of the end of the wire. To understand the actual physical dynamics inside a conductor, we have to abandon that top-line summary and adopt a localized, point-by-point perspective. This requires a more precise mathematical tool, a vector field known as current density, denoted by the letter J. Conceptually, current density tells us the exact amount of electrical current passing through a microscopic unit of area at one specific point in space. Because it maps localized flow, it has to be a vector quantity. It requires a magnitude to tell us how much charge is moving, and a direction to tell us exactly where it's going. We measure this density in amperes per square meter. The physical direction of the J-sector aligns perfectly with the local electric field that is actively pushing those positive charges forward. With current density, we stop reading the total output like a single thermometer and start mapping the exact weather system of electrical flow inside. To figure out how to measure this localized flow, let's start with the simplest geometric setup, slicing a wire perfectly perpendicular to its length. This diagram shows the ideal base case, a cylinder with a flat face sliced cleanly at a right angle. On it, we define an infinitesimally small area patch, dA, at point P. Its normal vector, n hat, points strictly perpendicular, straight out of the surface. In this perfectly flat setup, the charges are moving straight down the wire, which means the actual direction of current flow aligns exactly with our surface's normal vector. Because the flow and the surface are perfectly aligned, we get this foundational definition. The current density vector J is the derivative of current with respect to area, pointed in the direction of that normal vector. This formula is a perfect starting point. But real-world engineering often deals with irregular, slanted, or curved surfaces, which immediately breaks this simple alignment. What happens to the math if our measurement plane is sliced at a steep angle? A straight cut gives us a circle, but a 45-degree slice produces a long ellipse. The slanted slice's physical surface area is significantly larger. This diagram illustrates the slanted geometry's physics. Notice the critical misalignment. Our normal vector, n hat, points up and away at an angle theta from the horizontal current density, vector J. To find the effective perpendicular area, we project that slanted area using trigonometry, giving dA cosine theta. That expanded area goes directly into our modified density equation, dividing the microscopic current by dA cosine theta. If we multiply both sides to isolate the infinitesimal current fragment dI, we get this intermediate step, J times dA times the cosine of theta. Multiplying two magnitudes by the cosine of their angle matches the precise definition of a vector dot product. We rewrite it as J dot dA. Integrating reveals that total macroscopic current I is the surface integral, or flux, of the localized current density field. The dot product handles this geometric projection automatically, extracting the net flow through any arbitrary surface, regardless of how it is oriented relative to the field. Now that we have the geometric rules, let's apply this to a concrete physics problem involving severe non-uniform flow. This document lays out the parameters: a cylindrical conductor with total radius capital R. Inside, flow is densest at the center and linearly drops off outward. That non-uniformity is described by the equation J equals J naught times 1 minus lowercase r over capital R. Our mission is to integrate this localized density across the entire circular cross-section to find the total macroscopic current. Because the current density changes based strictly on its radial distance from the center, we slice the cross-section into infinitesimally thin concentric rings. To run the flux integral, we first need to define the exact surface area of one of these specific rings. If we snip the ring and unroll it, it forms a flat rectangle. the length is simply the circumference, 2 pi r, and the width is its infinitesimal thickness, dr. This proves the formula for our area element. The area of the ring is 2 pi r dr. Successfully identifying and constructing the correct geometric area element is the absolute prerequisite for solving any complex flux integral. With our area defined, we substitute the density formula and constructed ring area into the flux equation. To capture the entire wire, we set definite integral bounds from the dead center, radius 0, to the outer edge at capital R. We simplify by pulling out constants and distributing the r variable, splitting the equation into two simple polynomial integrals. Evaluating these using the power rule gives the terms inside the brackets, r squared over 2 minus r cubed over 3r. After a final algebraic cleanup, we arrive at the exact total macroscopic current flowing through this wire, I equals pi times J0 times r squared, all divided by 3. If we ignored this radial drop-off and assumed the maximum density, J0, was uniform across the whole area, our total current would be pi times J0 times r squared. That estimate is 3 times higher than the actual flow we just calculated. Mapping the localized vector field of current density allows us to analyze complex phenomena where flow is never uniform, from the skin effect in high-frequency AC transmission to the precise charge distributions within plasma containment fields.